Hello everyone. Today I will show the solutions to the Prairie Math League High School round 131, problems 5 and 6. For problem number 5, we wish to find the 97th rising number. Rising numbers are all such numbers that have distinct increasing digits. So, we're going to solve this problem in a bit of like a tedious way. We're going to find each digit one by one. So we start with the first digit. If the first digit is 1, then we have 4 spots and 8 possible numbers that we can put in these 4 spots from 2 to 9, which can happen in 70 ways. Now notice that 97 minus 70 is 27. This means that all such numbers with first digit 1, this doesn't include the 97th number. So we have to sort of backtrack. So, on the other hand, if the first digit is 2, then we have, again, 4 spots, but this time the numbers from 3 to 9, which is 7, so 35 ways. Now notice that when we take this result and subtract the number of ways starting from 2, we get a negative number. What does this mean? Well, that means that all the digits that start with, all the rising numbers that start with 2, this does indeed contain the 97th number. So we have verified that our first digit is 2. Now we move on to the second digit. We apply a very similar argument. If this is 3, then we have 3 spots to put 6 numbers from 4 to 9, which is 20 ways. And after doing the subtraction, we get 7 ways remaining, which is still positive, so we need to go on. On the other hand, if this is 4, then we get a negative number, and as we showed above, this means that the second digit is indeed 4. Now we go on with this very much the same process, except that instead we have 2 spots for 4 numbers from 6 to 9. And after a bit more, we see that the third digit has to be 6, as we can see here. However, do we notice something? Do we really need to keep on doing this? Well, no, because remember, rising numbers are always increasing, and here we skipped over the number 5. Where is 5? It's not here. And this means that since 5 is one of the options, this means that the answer is 5 because we skipped it. So the answer is B. Now for problem number 6, we have 2 adjacent semicircles, 1, 2, and their common external tangent passes through vertex D of rectangle ABCD. And now we need to find the ratio for which the common tangent divides the side BC. So either this to this or this to this. So now this problem is quite it requires several steps. So first we're going to label the radius of this as A and the radius of this as B. Whoops. This is B. And this is B and this is A. Now we can use Pythagoras' theorem, which, if we notice, we can drop a perpendicular much like this diagram. And here we have this is B minus A, this is A plus B, and we can apply Pythagoras' theorem to get that this is 2 squared of AB. So this is also 2 squared of AB. Now we're going to apply something else. We have power of point, which states that if we have, one of the variations of power of point is that if we have 2 tangents from the same point to the same circle, then this side length is equal to this side length. So here we see that to this circle, we have 2 tangents. Oh yeah, this is from M, which we're going to denote the intersection point of the 2 semicircles. We're going to rise a perpendicular, and it's going to hit RS at N. And here we have that this is equal to this by power of a point, as we just saw. And similarly, this is also equal to this by power of a point. Therefore, Rn is equal to our ns, which is, since their sum is 2 square root of ab, each of these is ab, and this is also square root of ab. So, now we're going to do a few more things. So, as you can see, this is quite complicated, but basically, we've introduced a lot of new points here. R is the, if you drop the perpendicular onto xd, and where x is like the intersection point of the two lines, DE and AB. But anyways, R is like the base of this altitude. S is the base of this altitude, and we've labeled the centers P and Q. M and N you saw. And we're also going to drop perpendiculars from N to U on AD, from E to V on MN, and from B to T on PR. Now, what do we see here? Well, the purpose of these lines is to create like a whole bunch of similar triangles. For instance, BEX is similar to SQX, and it's similar to a lot of other stuff, but they're basically, they have a common angle here, or in the case of other things, have equal angles. And these angles are equal because this is a right angle. So okay, so we're going to try to list at least some of these triangles. This triangle, this triangle, this triangle, this triangle, and this triangle are all similar because they share the common angle, angle BEX, this one. And it's also similar to this triangle, and this triangle. Not necessarily in that order, but anyways. Now, why do we need all these? Well, we're going to find AD and BE based on these. So, AD is this one. And notice that AD is equal to this plus this. Now, since this is these are 90, this is a rectangle, so AU is equal to MN. DU, on the other hand, is equal to UN times, times PT divided by BT by similar triangles. So here we see AD, DU plus MN, and MN is just square root of AB, as we saw above. DU is equal to UN, which is 2A, times PT divided by BT. All of this is by similar triangles because BT is similar to D and U. And we can do a bit of algebra of this. This is equivalent to this, and these cancel out. And we're left with A squared over square root of AB. Now, BE is a very similar process, and this process is quite tedious again, so I'm not going to go through everything. But you just see that it's, again, we're using PTB, but this time we're applying this to find BE from NVE. Oh yeah, V is here. But anyways, we get B squared over square root of AB. Therefore, we can get CE over BE, which is this here. BC, CE is equal to BC minus BE. And we can do a bit of fraction simplification with that. Now, AD over BE is this over this, which is A squared over B squared. And at the end, we get a squared minus b squared over b squared. So this is answer choice A. And we're done. Thank you for watching.